So what if I told you the solutions that we have today in AI are quite limiting? And why do I say that? Because most of the solutions or architectures, especially for the AI algorithms, they're quite powerful. They're solving several problems. But unfortunately, they're still not great at solving problems that require real-time decision-making, let's say within less than a second. They're not great at continual learning. They're not great at working in novel or unknown scenarios, nor they're great at energy efficiency. This is one of the discussion topics in this Edge AI foundation. And if we look at these solutions, one of the reasons is because they are perhaps monolithic. Perhaps we are driven by performance in different situations or scenarios. Maybe there are opportunities for us to look at other ways to solve these problems. And one such solution could be neuromorphic computing. Can we get an advantage by using neuromorphic computing as a solution in this space? So specifically in my research lab, we are very curious to design the next generation AI systems that are capable of performing natural tasks similar to how humans would solve these problems. But the main reason why we are interested in looking at biology or neuroscience or biological systems in designing these algorithms or hardware is because we are interested in solving these problems in the most energy efficient way. So if you look at this cartoon here, we really have to work very closely with the neuroscience researchers to understand the plasticity mechanisms of the brain, abstract those principles, design new algorithms, take these algorithms and port it or deploy it on different hardware systems, existing or newly designed hardware systems. And we have some startups here who are focused on this, like Inatera or BrainChip. But what exactly is neuromorphic computing? There is no 100% consensus in the community about this. But in general, any system that closely emulates or mimics the structure and principles of biointelligence that are often developed by neuroscientists in order to design efficient computational systems. And we are often guided by constraints in size, weight, and power. That rings a bell, right? For this audience, it's very important because you are designing solutions that are for these edge applications that are constrained in the size, weight, and power environments. And you can think of aspects of these principles that kind of fit neatly in the center of some principles drawn from machine learning that is amplified or made efficient by using neuro principles, or some architectures that are made efficient by using these biological principles. And really the field is on an innovation trigger, or we would like to call it, it's having its own AlexNet-like moment right now. And you can see the growth potential for neuromorphic computing in the coming years. And the systems themselves, I mean, the hardware for the neuromorphic computing community has grown significantly in the recent years. So, oops. Okay, let's see. The animation doesn't seem to work, but the plot looks something that is growing exponentially here. So we have billions of neurons on these chips today, starting from few neurons. Today's neuromorphic chips have a significant number of neurons, about 5.2 billion neurons from Spinnaker and Intel Loihi's large-scale systems. And we anticipate by next year, perhaps there will be systems that will have 10 billion neurons. Why do we care about having 10 billion neurons, 5 billion neurons? What does it even mean for compute? What does it mean to continuously increase the number of neurons on these systems? This is just one measure of what you can accomplish on these systems in terms of the complexity of algorithms. but it doesn't mean it necessarily solves the problem in an efficient way. But this is just one measure in which the community looks at the growth in neuromorphic computing. I'm sorry the plot is not being displayed, but this is published in a Nature article that came out last month. You should be able to access it there. So why exactly we want to focus on neuro-inspired learning? So brains are the best working exemplar models that we are familiar with, and they're really efficient at processing unstructured dark data and continuously making predictions. But if you look at that main aspect, like if we look at as computer architects, this is amazing at what's happening in the brain. The hardware is not hardwired. There is plasticity at all levels of abstraction. Whether you're thinking at the cortical regions, whether you're thinking at the synaptic level, the neuronal level, or at any singular abstraction, even at the neurotransmitter level, there is plasticity. And this gives it amazing ability to adapt and learn in novel situations or adapt and learn continuously through our lifetime. But how do we bring this kind of plasticity into our learning algorithms or into our hardware? And faults are indigenous in this system in a sense. If you think of the individual synaptic spikes, how they spike, it's probabilistic. Individual neurons are not precise. So there is a lot of probabilistic or stochasticity embedded in these individual components, but in the end, these systems seem to be working very efficiently. How often do you think humans, once we learn how to enter a door, that we would just jump through the window, unless the situation demands? We are pretty good at not making these mistakes. We are very good, once we learn a situation or learn in a certain environment, we do not do these mistakes. So the reason is there seems to be a lot of parallelism and redundancy in the brain that appears to compensate for this probabilistic or stochastic units that you might have. And it really works very well with imbalanced data or dark data, as I mentioned. And just to give a little bit of context, I don't have to preach to the audience here as to how the cost of computation is growing in the AI community. It's doubling every 3.4 months. And the compute cost is decreasing, but the cost of training some of these models has grown significantly over the last couple of years, ranging anywhere from $10 million to $50 million to some of these models. And I've heard from several of the companies yesterday where you are trying to optimize using quantization model compression techniques, using new types of architectures to address some of these challenges and compress the models so they can fit on your edge devices. But if you think of more features that need to be added into this, especially in the edge domain where you're deploying these things as sensors in environments where humans are not easily able to access, then you would want to do some kind of real-time decision making. Then perhaps just compression is not alone sufficient. Maybe there needs to be a fundamental rethinking in how we are designing the architectures and algorithms. So if you look on the contrary, the cost of computation in brains, I mean, this can be debatable in what is the exact wattage or exact power that the brain needs, but some estimates show that you probably need only 0.1 watt for some of the most critical computations, higher order decision making that we do as humans. So if you look at that, that is remarkable. And we are nowhere close in silicon or in the hardware to get to this level of efficiency. And there are also suggestions that overall it could be 20 to 25 watts of power. This prediction engine is only taking that much of power. So how do we kind of abstract some of this efficiency into systems or into algorithms? So when we were working on this neuromorphic computing article for Nature, we worked over a 2-year time frame in thinking through what are some of the core features we need to adopt in order to build these kinds of systems. There are several researchers who have, from Dr. Carver Mead's time, who has coined the neuromorphic computing field. There are several researchers who have identified what those features should be. But when you're trying to think of commercial scale or when you're thinking about production, I think there are several other aspects to think about in how these solve the problems. So if you look on the left here, we are talking about the neuroscientific principles that are guiding us to get these abstractions into the neuromorphic hardware that would help us in building algorithms with certain features. Of course, we want them to be sparse, extremely sparse, scalable, and you want to have distributed and hierarchical architectures. You would want to have these systems to be reconfigurable. And I have lots of debates with my colleagues who work on FPGAs. Well, we already have that. FPGAs are reconfigurable, so why do you want to think about that as a challenge? But we are talking about really runtime, fine-grained reconfigurability. When you want to have new synapses that are generated or new synapses that are pruned dynamically at runtime, we do not have that kind of fine-grained reconfigurability in our systems today. And perhaps asynchronous communication between the neural processing elements, and in general, we would want these to support heterogeneous processing and interaction. So, well, it's not an easy process to get to this end solution, but there are ways in which we can look at biology again as a source of inspiration, I said. So one example I would like to give, I hope this video plays. I don't know if someone can help play the video. But this is a great example where you see in biology, including us as humans, we find it really hard to do operations in mathematics very quickly, whether it is division or multiplication or any of these operations are very hard for us. But we are continuously predicting, processing, identifying patterns, detecting patterns, and classifying in that sense. Whereas the compute systems are really good at the mathematical processing. So whereas they fail in terms of learning continually, even trying to, if you see some of the robotic platforms and how they're struggling today to do some of the simple processing in placing objects in different environments or so forth, or walking and navigating through complex environments that have changed from one situation to the other. So biological organisms seem to adapt to these changes very naturally, very quickly. And there is perhaps no single feature that enables them to do this. There's a combination of features that help humans or other biological organisms to solve this efficiently. I guess we are not going to be able to play, or, oh, okay, just a second. So this is, in this video, we are trying to show how a squirrel, which is unable to cross that path initially, it is assessing how it should be able, what is the best way to cross this path, and it comes up with a unique solution very rapidly and tries to address the problem. Perhaps we will go to the next slide. That's a cool video. I wish we could have watched it. So in a sense, what we did was, well, because neuroscience is a vast field, there are several biological principles that can be adapted to build this efficiency in algorithms or hardware. So initially, we were thinking perhaps looking at what are the foundational building blocks to build a neuromorphic system might be the right approach. But today, the way we look at it is, can we anchor it in a problem that is of interest to both the machine learning community and the neuromorphic or neuro-AI community, and see if we can address this problem in a better way using biological principles? Maybe that would be a grounding place for designing better architectures. And that's the problem we are looking at, which is called either continual learning or lifelong learning, because it is considered as a key aspect of intelligence and one of the grand challenges even in the machine learning community today. So When we were working on this DARPA project on lifelong learning, there's this cartoon we have built to show in a simple way how conventional AI models today fail at this problem. So if you look at this red line here, that is showing how the performance of this model, which could be any of your existing models, transformer-based models, or any of the architectures, how they work versus what we would ideally like a continual learning system to do. So if you look at the performance, when a new task is introduced here, the conventional AI models often drop in performance, catastrophically fail, or express some random behavior which we do not prefer in that situation. Whereas ideally, what you would like is perhaps there is a small refractory period where the model is learning and then bounces back and has higher performance in that context. And then similarly, another new task is introduced, you see the same thing. That is one aspect of it. An even bigger challenge here is if you reintroduce the previous task again to the model, you not only want it to perform better or perform at the same level as it did in the past, but you want it to perform better than what it did in the past. The reason is if you look at the current models, if you introduce the previous task in a sequence, they often fail at that task because they're not able to retain that knowledge. And this problem is called catastrophic forgetting, and this is one of the problems that the community works heavily on in a continual learning space. Though there are several other features you need to look at, but this is one problem where we are looking at more actively what the solutions could be. So we think there could be a variety of plasticity mechanisms that could help us solve this problem. So during the DARPA project, we come up with what are these features that we would like to have for this continual learning system. One is, like, if you look at the top cartoon here, this is a robotic arm where, it's doing a task A, picking up an object, and then dropping an object, task B, task C, packing this box, and then you reintroduce some other task here, which is task B. So these sequence of tasks, let's say, are introduced to your model. These are some of the features we really would like the model to support. One is it needs to be able to transfer and adapt to the situation. Let's say we give the model a variant of task B, which is instead of the square object, you are dropping in some other shape in here, and then give a variant of task B again, and a variant of task B again here. It should be able to perform at the same efficiency as it was able to perform for the task B initially. So it's just like learning or transferring the knowledge it has from how it performed on the task B to these variants. The second problem, which I already talked about, is overcoming catastrophic forgetting. So when you have task A and then the model sees task B and you reintroduce task A, often it does not do well on that task A. So what you would want the model to do is work efficiently on task A and not forget the information. So you do not want to have that catastrophic interference in your model. And also task similarity, when you look at task B here, you could decompose the task into robotic arm positioning itself, gripping, and translation. And if any of these subtasks are introduced to the model, or if there's a different task C here, which has parts of this task B, the model should be able to identify the similarity between the tasks and still do it efficiently, learn efficiently. And this is a hard one, task agnostic learning. A lot of continual learning models today, the way they're evaluated, because it's a hard problem, how do you actually evaluate a continual learning system? These are artificially created environments that we are evaluating these systems on. But task agnostic learning, especially how models are evaluated today, is the model exactly knows when the context or task switch is happening, that you are trying to detect or solve task A versus task C. The model exactly knows when that switch is happening, but in real world, you do not know when that switch is happening. When a new object enters your environment or when your environment changes, you often do not know when this happens. So you need to be able to learn in a task agnostic manner. And also in the presence of noise that you haven't seen in the training, but it is there in the real world deployment. It should still be able to work effectively. And this is something perhaps this community cares deeply about. How do you do it in a size and form factor that is sustainable and in a resource efficient manner? So I think looking at neuroscience principles or neural plasticity in the brain could inspire us to design new learning algorithms. And perhaps this is something maybe not of interest to this community, but there's a lot of interest in the neuroscience community in how to validate some of the theories they are building using these models or the hardware systems that are designed. So I'll give you examples of 3 different mechanisms that were incorporated in one of our algorithms that tries to do continual learning. So the first feature is what we observe in the brain called metaplasticity. It's the ability of the synapses to change their own plasticity mechanism. So this helps us to modulate the synaptic efficacy in the learning, and this would help us give a lot more finer granular control beyond the synaptic weight, which is what you use in most of the learning algorithms, to help us learn in situations where you need to retain the information or emphasize the information that it has learned in the past. The second feature is synaptic consolidation. And this is something that helps in retaining information over a longer time frame. And I think I'm running short of time. No? Okay. And the third one is neuromodulation, and which is it's a mechanism to boost learning, and it helps support, address the catastrophic forgetting that I've talked about, and try to help the model learn in unknown or novel scenarios. What some of these mechanisms are essentially doing is that they're encouraging the synapses or neurons that are not participating in the learning. They're encouraging them to participate, boost them and support them and say, well, I want you to participate in this learning process. And the neurons that are hyperexcited or overexcited, they're trying to stabilize them and say, well, perhaps you need to not be as excited. In a sense, we reduce the threshold or increase the threshold for those neurons' participation in the learning process. So this is like, these mechanisms give us a lot of finer granularity in terms of control of our learning algorithms, in a sense that we can work in the local domain, not necessarily in a global domain. And that is really advantageous when you're thinking of algorithms for the edge. Okay, so what we did was, this is a student of mine, Nick Soares, did for his PhD. He took some of these metaplasticity and synaptic consolidation mechanism and built it into a spiking neural network. I've seen some presentations on spiking neural network, I think by Natera yesterday. Here, what you're doing is, this network is not very deep. For those who are used to these deep networks, this network is not really deep. You only have 2 layers, and these layers are incorporating some special types of neurons. You see 2 shaded areas, so each of them have 2 compartments with some special types of properties. And I'm happy to chat about the whole algorithm or the network after the talk. And we use surrogate gradient learning rules along with this metaplasticity and synaptic consolidation. And this model is able to solve the continual learning problem on smaller data set, but it is one of the first models that was demonstrated in the community with very simple overhead in terms of metaplasticity or consolidation. And it does this in a task agnostic manner. That's where the course name comes from, and also because we are from San Antonio. And it is able to do it in a single epoch. That's the beauty of it. Task agnostic, and in a single epoch, it's able to learn very efficiently. And this is another absorption of the neural metaplasticity developed by a student who is attending this conference, Anurag. He developed something called NEO, again, in the same way to address the continual learning problem. In the interest of time, I'm going to forward here. So what makes this neuromorphic computing system successful? And as I mentioned, we've been thinking about this for a while. And I've heard even reservations about neuromorphic computing because it's been there for a while. It hasn't shown success in a commercial scale. It hasn't been adopted in a lot of real-world applications. I think things take time. I think, as I said, we perhaps are in that AlexNet-like moment right now for neuromorphic computing. And what are some of the things that are limiting us to get to that next stage? And that's what really we looked at in this article. I would encourage you, if you're interested in this space, this is a great article that, in a sense, that we have thought through what are some of the barriers that are stopping us from neuromorphic computing getting to its full potential. But one of the things is we really need to work very closely across the hardware and software stack. The reason is a lot of neuromorphic solutions are not adopted at the level you would see in a machine learning community because we do not have these PyTorch type of frameworks that people can just get in and start running a model in a matter of 5 seconds. A lot of things were started from grounds up, from the lower level of abstraction, so the software frameworks are not as mature or as evolved as in the machine learning community. So I think there are lots of efforts that are being happening right now, lots of universities and industry partners that are working on these different solutions so that we can have more engagement from the community to build robust solutions. And this co-design really can help us build better solutions. And for example, in the context of lifelong learning, it can probably make us think, how do I generate these new synapses on the fly? How do I generate new neurons on the fly? And how do I ensure that the replay that I'm giving to my network is done in the most efficient way? What is the type of memory I need to use? And this is all like a co-design framework you need to think of, whether you want a resource growing solution or whether you want a resource constrained solution. And this is one of the chips that my other student who is attending the event as well has developed in the continual learning domain, the problem which I talked about earlier, tacos. He has taken those principles, and we did not do one-on-one matching with tacos. We have kind of simplified the algorithm to design this chip, and it supports a custom data flow that he's introduced using AER, and several of you might be familiar with these type of architectures that you use in the ML architectures. But I think one of the things is, again, it is able to solve this problem in a task-agnostic manner. And before I wrap up, I just want to shift gears and want to bring something to the attention of this community. We just launched a project with support from NSF. We are going to create this neuromorphic hub or neuromorphic commons for US. And that will be, that's officially launched right now, and we are in the process of negotiating with industries and also trying to build that open source community. So the idea is to really develop and deploy this large-scale neuromorphic infrastructure that the community can actually take advantage of. Right now, it's not very easy for startups or young researchers in smaller research labs to access these platforms. So we want to bring this or democratize the access to this neuromorphic computing platform. And through this process, we would want to support open source software design frameworks. And we will hopefully partner very closely with the Edge AI Foundation in this effort and have common benchmarks. And I think there is a community effort right now that's going on. And also develop new types of hardware software co-design frameworks. These are the leads. Again, we are only the front faces of it. We are going to have probably hundreds of researchers who are going to be engaged in this effort. And some of you might know Vijay, who's very actively engaged in the Edge AI community. And where do we think we could benefit in partnerships with industry? Definitely in the application domains that I'm highlighting here, whether it's in robotics, healthcare, neuroscience, high-performance computing, or of course in AI machine learning. But I think there is opportunities for us to do these things collaboratively in terms of hands-on training, community challenges, or benchmark competitions. And one aspect of this Thor framework is also to work with the NeuroBench community, and that's where Vijay's collaboration comes in. I think Charlotte and Vijay has worked on this effort in trying to build benchmarks that would help evaluate neuromorphic systems for their efficiency. And we have two different tracks in here in the algorithms or systems based on whether you have a neuro-inspired algorithm or a neuromorphic computing system. And one potential success case I'm personally invested in is in healthcare because of our strong partnership with our physicians and clinicians in the Matrix Consortium at San Antonio. But I think there are lots of interesting use cases for neuromorphic community or for Thor. So with that, thank you so much for your time and for this amazing team who supports me in doing all these adventurous projects, and for our sponsors.